Okay, so welcome everyone to today's webinar. It's going to be the last session with two presentations for this season, and it's a great pleasure to introduce the first speaker of today, Taylan Kargin. So Taylan is a postdoc at MIT, and he recently received his PhD from electrical engineering at Caltech. Technical University in California, under the supervision of Bobak Hasibi. His research is on control theory, optimization, machine learning, and trying to apply robust and adaptive control of dynamical systems under uncertainty. And here he's going to talk about non-rational control. So without further ado, I want to give the control of the mic and screen to you, Tyler. Thank you for being here. And yeah, it's all yours.
Oh, okay. Thank you very much, Ahmed Reza. Thank you for having me today. I'm going to talk about my PhD research um, uh, on non-rational control. This is about a unified approach to robust control, specifically distribution robust control in the infinite horizon setting. Without further ado, let me just go ahead and okay. Um, Let me start with introducing the setting. So the setting is the linear quadratic control. Let's suppose that we have a system, a dynamical system. The system it evolves according to this linear dynamics. So xt is the state with dimension dx, and ut is the control input, and w2 is the disturbances, external disturbances. And the goal of the ADA and this system is controlled by a control agent, and the control agent essentially decides what control input to choose according to past observations. And in this setting, I'm going to assume that the control agent is able to observe the disturbances, the external disturbances, without loss of generality. So this is if you're familiar with control, maybe you've heard of state feedback setting where the agent observes the state. So this is quite similar, since once you observe the state, you can also estimate or guess what the disturbance is. So for simplicity, I will assume that. And also, I will assume for simplicity without and loss of generality that the policy of the control agent is a linear policy. And the disturbances follow a probability distribution, P sharp. And this is and we don't necessarily assume that the disturbances are independent or IID, so they can have arbitrary correlations over time. And the goal is to essentially minimize this quadratic cost function that depends on the control policy as well as the disturbances. And in particular, we're interested in the expected cost throughout the control process. So this setting is quite general and is well known in control, but in most settings, it's assumed that the distribution of the P sharp of the disturbances are known. But what if they are not known? So in standard setting, what people do is even if they don't know the disturbances, they gather basically samples from this unknown distribution, P sharp, and then from those samples, you can construct a nominal distribution. So either you can do this by simply just building a histogram through the empirical distribution, or you can use your favorite machine learning algorithm to construct a more sophisticated distribution or sophisticated model. But essentially, the the unknown distribution and the constructed nominal distribution are different. So there's a distribution shift happening here. And what happens if we use the nominal distribution to design the controller? So the consequences could be fatal, as in this case, where a self-driving car in Tampa, in Arizona, hit a pedestrian, thinking that at night, because a jaywalking pedestrian, and the car didn't recognize the pedestrian because the pedestrian was jaywalking and it was at night, and the classification basically wasn't persistent enough. So the automated system didn't track. So these kind of and in these settings, relying purely on the nominal distribution and disregarding the distribution shifts can be unsafe and even fatal. So this is the outline of the rest of the talks. I already talk about the distribution shifts, and I will go through the stochastic, adversarial robust, and distribution robust control. I will present some simulations, and I will go through the steps of how to derive the infinite horizon distribution robust controller in the second part. Um, so the stochastic control and adversarial robust control are basically two extreme scenarios in this spectrum. In the stochastic setting, if we use just nominal distribution to design the controllers, then we basically do this expected minimization, solve the expected minimization problem. Whereas in the adversarial setting, the assumption is that we don't know the distribution of the disturbances and their adversarial. So instead, we're trying to minimize the worst case cost among all possible realizations of the uncertain disturbances. And in these two settings, we get in this spectrum, we see that, well, okay, the stochastic controller is maybe better, shows better cost performance and is more optimistic about uncertainties. But at the same time, it is sensitive to distribution shifts, as we just seen, and can be unsafe. There is the adversarial robust controller, which is exemplified by H infinity control, for example, is more pessimistic about these uncertainties, and therefore the cost performance is more degraded. But we are more robust and safe at the expense of this degraded cost performance. Whereas in real life, we're basically somewhere in the middle. It's never that the true distribution is completely different than the nominal distribution, or we're never necessarily in this worst case scenario. So we need a new control design method strategy that can mitigate such distribution shifts while balancing the performance and robustness and safety. So, and as an alternative, in this talk, I'm going to consider the distribution robust control setting, which is essentially a blend of these two regimes, where we, instead of minimizing the expected cost under the nominal distribution, we're going to minimize the expected cost under the worst possible distribution within an ambiguity set. And here, this set is what I call the ambiguity set. It is centered around the nominal distribution, and it has a certain radius. And we believe that the true distribution lies somewhere within it, but we don't know where it is. So this is essentially blending these two regimes. And specifically, I'm going to consider the Wasserstein distance to measure the discrepancy between the true and nominal distribution. And Wasserstein distance is given by this formula. It is the optimal transport cost. And specifically, this is the L2 version. And the reason I'm focusing on the Wasserstein is because it is tractable, but also it is more expressive in the sense that it can encapsulate both discrete, continuous, and all such mixture distributions. So the full information setting of this problem, where the controller observes the state perfectly, has been proposed and solved by Taha et al. In 2023. And the partial information setting has been again solved by our group in 2023. And in both cases, this problem and this distribution was control problem in the finite horizon setting. And here, capital T, I might have forgotten to say what it is. Capital T is the horizon. It reduces to a semi-definite program, as shown here. But the difficulty here is that this semi-definite program scales with the horizon t. So if you have, let's say, 100 time steps and you need to solve this problem, it becomes impractical to do that in real time, which is what we need to do if we want to run this in a, let's say, autonomous car, right? It has to be solved in real time. So then basically the message here is that the finite horizon Wasserstein distribution reverse controller becomes computationally prohibitive for any practical real-time implementation. And so there are several works in exploring Wasserstein distribution reverse control in both finite and infinite horizon settings. So in the past, most of the works that have been proposed consider the disturbances to be independent, but unfortunately, this is not quite realistic in the control setting, because the disturbances that we see are going to be mostly time correlated. They're never going to be actually independent over time. This is going to be a naive assumption. And even in the cases where there is correlations, when the correlations are assumed, the finite horizon setting, as we just discussed, becomes intractable to solve with STPs. So that's why in this talk, I'm going to focus on the infinite horizon setting. And in the infinite horizon setting, the claim I want to make is that the problem turns out to be actually much simpler, not much simpler, but the computation complexity actually reduces. Um, so overall, basically, the infinite horizon Wasserstein distribution reverse control can be implemented efficiently, and it ensures and guarantees stability, while at the same time balancing the robustness and performance informed by the available data. Okay, so let me show you some simulations to convince you that the infinite horizon Wasserstein control is much better actually than the finite horizon. So here what you see are four different time domain experiments where in the x-axis you see the time, and in the y-axis you see the average cost, average accumulated cost. So it is average over time. And in each setting, we are exciting the system with different disturbances following different noise patterns. From white noise to worst case noises generated by the underlying controller. And in the black curve is the distribution robust infinite horizon controller that I'm going to that we derive that we proposed, and the purple and the red curves are the finite horizon. versions. So since the finite horizon controllers require us to solve an SDP, we cannot actually solve this SDP for the entire duration of 200 time steps. Our computers actually even don't allow. So what we do and what people do in practice is they solve in a receding horizon manner, also called the model predictive control. And we, in this case, I believe we solved repeatedly 20, these STPs for 20 time steps. And as you can see, the infinite horizon controller actually performs much better. The cost that it incurs is better than the other two, the finite horizon cases. And it is also much stable. You don't see uh, these like kinky peaks and so on. And this is something we really desire in control because we want the system to run very smoothly. So if you ask me, well, okay, that's nice, but how does the worst case distribution actually look like in this setting, and depending on the nominal and the radius? And essentially, the radius of the ambiguity set determines our level of confidence. So the smaller the radius is, the more confident that our nominal is close to the true distribution. The higher the radius is we are less confident. So in this in this slide, I'm showing you the of the worst case distribution. So I'm assuming the nominal disturbance is a white noise. And here, the worst case disturbance in that setting happens to be a stationary Gaussian process. And a nice way to represent stationary Gaussian processes over discrete time step is to plot its power spectral density, which is given by this Fourier transform formula. And for white noise, essentially the frequency, every frequency is equally probable. So you would see that in the PSD plot as a constant at the level one. And once you increase the radius, then you tend to see these peaks appearing. So that this tells us that once our confidence decreases, which basically means the radius increases, the worst case disturbance happens to take this shape. And if you take the radius to infinity, then you end up with two Dirac deltas at these peak regions, which gives us the H infinity controller. Okay, so um, th so this is essentially the simulation results. And if you're still interested in how we get all these plots and so on, then I will show you the derivations and how we solve it. So um, in previously we talked about the finite horizon control, but now I'm going to move on to infinite horizon setting. So in the infinite horizon setting, to make things a little bit more simpler to handle, I'm going to use the operator notation. So in this notation, I'm basically stacking up the entire control states and disturbances as infinitely long vectors. And once I do that, the mapping between the controller to the state and the disturbance to state essentially becomes an infinitely long matrix. And specifically, it becomes an infinitely big Toeplitz matrix where the diagonals are constant. And also these matrices are lower triangular, and I will call them as causal, which means that the future doesn't impact the past. And similarly, I can represent the controller as a linear mapping, where disturbances to the control input. And once I expand this in a vector matrix notation, it becomes an infinitely long matrix, an infinitely long vector. And this infinitely long matrix of the controller is again a Toeplitz matrix where the diagonals are constant, and it's also causal. And also, I'm assuming that this is that the controller is linear and time invariant, but this is without loss of generality. Even if you consider the nonlinear controllers and so on, it turns out that the linear controller is still the best. Okay, so once we have this notation, now we just basically have these operators that we can treat them as simply basically like matrices. Once we collect the expressions for the system dynamics and the control, then we obtain the closed loop mapping, which is basically the mapping from the disturbances to the states and the control when the controller is given by K. And all of these operators also have frequency domain expressions given by these z-domain formulas or frequency or Fourier transform formulas. And the beauty of this formulation is also that the cost becomes the expression for the quadratic cost is simplified. And we can simply write it as this quadratic expression involving only the disturbances and the closeup operator tk. And here the star is nothing but the adjoint or the transpose. So the stochastic control exemplified by LQG and H2, as well as the robust H infinite robust control in the infinite horizon setting, can be equivalently represented as optimization problems in this infinite dimensional domain. And here the trace of the operator is defined by this integral formula. And the H2 norm and H infinity norms are essentially analogous to Frobenius and operator norm. And the nice thing about these two formulations is that they reduce to finite, the optimal solutions to these problems, the optimal controllers, essentially reduce to finite dimensional state space formulations given by this example. So similar to the standard LQG and H infinity control, we can reformulate the infinite horizon Wasserstein control by this minimization problem involving the average worst case expected cost, where the limit is taken over the time horizon as it goes to infinity. So the first question you might ask is, well, okay, how do we solve this problem? Like, is this a convex problem? And it turns out, yes, it is actually a convex problem. It reduces to a finite dimensional convex program. And can we solve efficiently? Yes, since it's finite dimensional convex program, we can actually solve it efficiently. And the third is, can we implement it using a finite dimensional controller similar to this expression? It turns out that it is not the case exactly. The optimal controller turns out to be a non-rational, meaning that there is no finite dimensional state space representation. And that's a challenge, and it is an inherent difficulty. But it turns out we can also actually overcome this by essentially approximating the non-rational solution or the infinite dimensional solution with rational ones through rational approximations. And we can even come up with suboptimality guarantees. So since I'm running out of time, I will go through the rest of it a little bit more quickly. So first of all, we can reduce this to a convex problem. This like highly complicated expression involving the limits, the max, and the expectation and the cost turns out that this entire thing reduces to a single minimization over a scalar parameter gamma, and we can write everything in terms of the closed-loop operator, closed-loop transfer operator Tk, and the nominal covariance operator M naught. Okay, so that's nice, but this is still an infinite dimensional optimization. So how do we solve it? And how do we tackle the causality constraint? So before I move on with how to solve this exactly, I want to first derive a simplification of this problem. And the approach is a duality formulation using a Fenchel conjugate. So this complicated expression involving the closed-loop operator, and you see the quadratic expression here essentially. This entire thing is essentially equivalent to, it can be written as a maximization using the Fenchel conjugate. And the advantage is that it sort of linearizes over the worst case disturbance. And we see that this maximization is a constraint optimization where the constraint is this Beerus-Wasserstein distance constraint. The Beerus-Wasserstein distance constraint is nothing but the Wasserstein distance between two Gaussian processes, where M and M naught are the covariance operators of the two Gaussian processes. And once we plug this expression back to here, then we essentially get a min-max formulation. And it turns out that we can actually exchange the min and max to obtain this dual formula. But the advantage of this formulation is that in the dual formula, once we move the minimization inside, uh, all we need to do is solve this minimization for the worst case covariance. And this minimization is nothing but the standard linear quadratic Gaussian control design. And we know how to do this. And all we need to do is finding the worst case covariance and solving a linear quadratic controller under the worst case covariance. So this is, yeah, basically summarizing what I just said. The entire infinite horizon Wasserstein control is nothing but a weighted linear quadratic control with an additional maximization. So I'm going to skip some of the steps here just to show you the end result. So it turns out that we can actually derive the worst case covariance explicitly, and I'm not going to explain the details of this complicated expression, but what I want to emphasize is that once you do this complicated analytical derivation, it turns out that the worst case covariance is parameterized, it can be expressed and fully characterized by a finite dimensional parameter. Here it appears as this gamma star, and it is essentially a matrix. Basically then tells us this complicated infinite horizon problem involving infinite dimensional operators and so on and so forth reduces to a finite dimensional convex optimization problem. So all we need to do is to find what that parameter is, and we can plug that in, and we can find the worst case covariance operator and the best controller, best distribution bus controller. And the way we do it is through a fixed point iteration. And also, I'm not going to explain the details right now, but essentially we can compute the worst case covariance at any frequency to arbitrary fidelity. Um, and once we obtain the worst case covariance, now the issue is how do we design the controller? And I just told you that the controller is not implementable. The optimal control is not implementable as a state space controller, the finite dimensional state space controller. So what we do instead is we approximate the optimal non-rational controller or the infinite dimensional controller by rational functions. And to do so, instead of approximating the controller directly, we approximate the worst case covariance because it turns out that rational approximation of this positive definite uh, operator of the positive definite transfer function is a convex problem. Unlike the general rational approximations, which are highly non-rational, highly non-convex. So this turns out to be very easy to solve, and we can solve it very quickly and then obtain a finite dimensional approximation with suboptimality guarantees, which eventually enables us to come up with near optimal finite dimensional controllers. Yeah, so and as I said, we can also guarantee the suboptimality gap, and we can well adjust how much with with how much additional states do we need to approximate the controller up to a given certain performance gap. And this is just to show you that the approximations that we obtain are actually pretty good, even with a small degree. Here, for example, the true controller is given by the black curve, which is not even visible. And the blue curve is the first order approximation. And the red and green curves are the second and the third order approximations. But you cannot even see here because the second and third order approximations given by the red and green curves basically almost overlap with the true controller, which is basically underneath this curve. So with very small degree of approximation, we actually get very good performance. So this is, and as a summary, this is just these steps that we follow to derive this result. And it turns out we can generalize this to even a broader number of objectives and just basically replacing the objective with these generalized objectives and using the Fenchel duality, we can derive controllers, finite dimensional controllers for arbitrary generalized objectives. So thank you very much for your attention, and please don't hesitate to ask any questions.